Good morning. Here's in America, and good afternoon there over in London. I'm John Leung. I'm a PhD candidate in computational science and informatics at George Mason University. And my research focus is in the group recommender system. My team, Dr. River and Dr. Kennedy, are associate professor at George Mason University. Both are the members of my dissertation research. And Dr. River also serves as my dissertation research director. Okay, I'm jumping ahead. All right, let me get back. Today's agenda, basically, I will follow the outline of my paper, but of course, I try to comment on the type of work that we are doing in the text-based, emotion-aware recommender. So, why we study the issues of making recommendations through an emotion-aware recommender? Well, basically, because making a good recommendation is hard, and making a recommendation that can be consumed by a user even harder. Consumed here, I meant, well, if you see a recommendation, let's say from a website, and you decided to take up on that recommendation, either to watch a movie or to buy a product that is suggested, then this is in the world of recommendation, basically that's considered a success. For example, making recommendations that are relying on the interaction history between users and items does not guarantee success, because users' tastes and preferences can change and shift over time. For example, a moviegoer has a history of liking to watch action movie, but may prefer a drama or even a Western for the night out. Humans' moods are dynamic and can swing abruptly. Recommender systems are mostly custom built and hardly transferable or adaptable between different domains. For example, a collaborative filtering algorithm deployed in a movie recommender cannot merely drop into a music recommender or book recommender or even a fashion recommender and expect the collaborative filtering algorithm to work without any modification. How then can we find a way to elevate the above limitation so that we can build a recommender that is adaptable to users' change in taste and preferences while addressing the cross-domain issue? We advocate that by incorporating emotion as features in the interaction between users and items, a screw to tie user emotions profile and items emotion profiles to an end-to-end multi-channel emotion-aware recommender to make recommendation while adapting it across multiple domains. Well, in this paper, I use quite a few notation, and I like to shortly brief over that so that you can follow my chain of thought a little better. We investigate in the paper the application of emotion profiles and of items and users, where items are movies and users are moviegoers. We denote MVEC, represent the emotion profile of a movie, whereas UVECs represent a user's emotions profile of all watched movie. We expand a movie emotion profile MVECs to include other features of the movie, such as movie genres information of movies, production team, directors, actresses, storylines, and other attributes in vector embeddings. We denote the expanded movie items vector as IVEC. In the same token, the expanded user emotion profile UVECs denote as WVECs. Our goal is to use movies and users' emotion profiles as components to build an emotional aware recommender for making movies recommendation to an active user. We obtain a movie MVECs using a Tweets Affective Classifier, we call it TAG, to classify the emotion profile of the movie overview. TAG is capable of classifying 6 primary human emotions of any subjective ratings. The 6 primary emotions are happiness, sadness, disgust, fear, surprise, and anger. We add a neutral mood to TAG for effective computing convenience. We built a comparative recommender platform which makes movie recommendation through recommender algorithms of content-based filtering and collaborative filtering. In the case of content-based recommender, we develop a movie genres recommender denoted as genres-aware recommender, or GAR. We apply MVECs to build a emotion-aware recommender, we call it year, and combine emotions and genres into a expanded IVECs and build a multi-channel aware recommender, we call it MA. So we also built item-based collaborative filter recommender and user-based collaborative filtering recommender. There's a lot of work already have done in the field of recommender in the past at least 20 years since the word of recommenders come into the existence. But before then, in the information retrieval technology, the recommenders work has been done well since date back long times, at least back in the 1950s, in terms of when the computers sort of start to, the automation start to sort of help out in the information retrieval field. So in the field of basic human emotion research, besides Professor Paul Ekman advocate the 6 basic human emotion which we are adopted Ekman's emotion classification in our work, Dr. Robert Bochat, the inventor of wheel of emotion, as depicted on the right side here, advocate 8 basic human emotion, such as joy, sadness, anger, fear, trust, disgust, anticipation, and surprise. Most of the emotion detections and recognition research are based on study of human facial expression or facial detection and recognition. We call it FDR. However, FDR has a drawback. It failed to classify and image emotional features in the absence of detecting a human face on the image. Thus, we propose to indirectly classify the affective features through textual-based emotion detection and recognition using movie overview, that is in our case. The challenge of our study in emotion detection from movie text-based metadata is to obtain a large enough movie metadata set with emotion labels. No such data set is readily available, so we therefore need to build the required data set by deriving it from 4 different sources. For the movie rating database, we obtain the data set from the Movie Land dataset, stored in the groupland repository. We scrape the movie database, TMDB, for movie overviews and other metadata. We derive our emotional word sense set as a contextual emotional word synonym from WordNet. Finally, we scrape the Twister database for tweets with keyword tag that matches our contextual emotion word synonym. Well, tag architecture is described as asymmetric double-decker butterfly wing bidirectional LSTM and CNN COVID-1D. Basically, here is a block diagram and try to illustrate the components of tag. We adopt a pre-trained contextual sensitive GoV word embedding to prepare the input for tag. We prepare two identical input embedding matrix with one pre-trained weights set to frozen and the other set to trainable. We input the embeddings along with the 7 emotional classes are fed to the first and second half of the butterfly wing architecture. The output from both butterfly wings are concatenated. The output is then gone through a CNN matrix pool 1D layer, flattened layer, fully connected dense layer, and output fed. Then the output is fed to a finally connect 7 neuron layer, with each neuron represent the emotion class as tags try to classify, and that is the output. The tag architecture, if you sort of look into it, it's a little more involved, and I'm not going to into detail, but this is the half part of the first half of the wing, and the double decker is the 2 bidirectional LSTM here that will feed into parallelly to a 7 set of COVID-1D layer, then concatenated, and then the output, that is the output for the first half wing. The second half wing is different. So the same input with emotional classes as input fed to the first decker of the COVID-1D. Instead of LSTM, now we use 2 set of COVID-1D, and then concatenate all the output. Then we fed it into 1 bidirectional LSTM, and the output is for the second half wing. So we concatenate the first and half wing, and then going through the other layers as I described earlier to get the emotional classification. So here is how tag in action. I selected a movie overview from the Godfather 1972. And here is the movie overview that it will feed into tag. The outcome of that is a probability distribution of the 7 emotion features. So with the MVECs affective feature, we call that is outcome, we call the movie vectors or MVECs affective feature probability distribution value. We can describe the Godfather 1972 movie as a film full of hate, because hate is the dominant feature that it detects. It is an angry movie. The content is disgusting because due to the violent nature of the film. However, the movie is full of surprises, but a sad movie. None can say that the movie celebrates happiness. So I just reciting the MVEC attributes that is ranked by the MVECs of the movie The Godfather 1972. Just by reciting the MVECs attributes, we explain the movie. On the same token, we can use UVECs of a specific user who watched The Godfather 1972 to explain how well the user has enjoyed the movie. Surprisingly, we can leverage the MVECs and UVECs as explanation or sentiment analysis tool. And that is that is a goodness of the using the vector, affective vector features can provide. So in terms of the data set, the MovieLens data set contain multiple data sets, each differentiate by the number of the rating the data set contained. And we sort of displace that on the upper left side. We use ML latest small data set as our training data set. The MovieLens data set do not contain metadata such as movie overviews or information about production teams, actor, actresses, director, poster, image, and others. So we have to scrape the TMDB for movie overview. We got over 430,000 titles from the TMDB. After we merge with MLAN datasets, the number of overview that can be shared by the two repository are depicted in the lower left table in a much sort of smaller scale as expected, because MLAN movie datasets do not track that many titles. The upper right table shows a sample of MVECs for movies. So we have here, a sample of 5 movies with the ID on the left, the dominant mood of the movie that tag detect is right near the middle, and the 7 emotional features, the probability distribution, or we call it MVECs, basically displays towards the right side. On the lower right side, we also depict an average mood varied WVECs for user ID 400, because we happen to choose this user ID 400 as a test user. And the UVECs that, or IVECs, WVECs that you see here, it is a compute from the means of all the movie that user ID 400 watched. It happened to be 43 movie that user ID 400 watched. In terms of our comparative platform, we utilize a few recommender algorithm. Cosine similarity happened to be the one that actually we are used throughout the 5 recommenders that we built. The important property of the cosine similarity is listed here. The maximum similarity when the angle between them is 0. They are originated in the same direction. They have 0 similarity when the angle between them is 90 degrees. They are orthogonal and one to one another. And they have -1 similarity when the angle between them is 180 degrees. They are originated in a dynamically opposite direction. We developed 3 content-based filtering recommender. The genres aware recommender, GAR, emotional aware recommender, year, multi-channel aware recommender, MA. And also in the content-based filtering, we want to determine how similar a pair of items are based on their meta tag. We can apply cosine similarity to determine how similar a pair of items are. And in terms of the collaborative filterings, we developed the attitude recommender in a comparative platform. In collaborative filtering, basically, it's a space out of a N by M rating matrix of N users and M items. For each element of the matrix ij represent how user I rated item j. Since we are working with movie rating, each rating can be expected to be an integer from 1 to 5, reflecting 1-star rating to 5-star rating. If user I has rated movie J, that you see the number either 1 to 5, and 0, the number 0 if the user has yet rated that particular movie. So after we actually generate a top 20 recommendation list by each of the recommenders in the comparative platform, the number that you see here are basically the movie IDs. And we have like a mapping table, which lists here for each of the movie ID that you see in the top end list. The title is, the corresponding title is next to it. With the test user WVECs against the list of IVECs from each of the top 20 lists, we compute the top 5 recommendation lists for each recommender. So what we mean here is simply this. Again, we depict on the upper right the average mood value WVECs of user ID 400. So here, this is the user emotional profile for user ID 400, and we use that to compute against each of the movies, the IVECs, and then we reorder them and rank them, and then we take the top 5, sort of item basically become our top 5 recommended list. And of course, the top 5 list is listed in the lower right side. Well, what we have planned for our future work is as follows. We plan to work on the multi-channel emotion-aware recommender by including other metadata such as poster images. And we also plan to apply the concept of emotion profiles for cross-domain recommendation making. We plan to use the user emotion profile to enhance the group recommender in our user grouping, group formation, group dynamic, and group decision making. In conclusion, we apply tag to generate a movie label dataset. We demonstrate the building of emotion-aware recommender. We develop a comparative platform with 5 recommender filtering algorithm to generate the top 20 recommendation list. We pick user for ID 400 as a test user, and we compute the WVECs for the user. With the test users WVECs, again, the list of IVECs from each of the top 20 list, we compute the top 5 recommendation lists for each recommender. And we find the top end list generated by Ga, Ear, and Ma show intriguing results. And we believe with further investigation, we could enhance Ear to make serendipity recommendation. The last item I want to say a few words, as you know, in the content-based filtering the recommender, basically the limitation of this algorithm of the content base is basically filtering is this. It hardly that it can generate any surprise recommendation. If you don't have the metadata there to compute, basically the recommender won't see it. So you will not able to generate any recommendation with the item based out of an unseen metadata. So we think actually the ear displays a lot of interesting sign that we like to investigate further for that issue. So here's a list of references I use in the paper, and again, thank you, and I'm happy to answer any question you have.